Alright guys, so taking a look at some notes here, a frame about the arithmetic and geometric, also the recursive and explicit. So we're kind of giving you an idea of what everything's going to look like to begin with. We're going to do these a piece at a time, okay? So you're going to be following along with me, and if you need the guest teacher to pause the video, if you're in class, if you're watching this at home, obviously you can pause it yourself. But if you're in class here and you need a little more time to write something down, ask them to pause it, okay? So we got our work cut out for us. But don't worry, okay? I wrote all the stuff once, and now I get to write it a second time. So you guys are in luck. You'll only have to write it once, okay? So let's start with this side, okay? We'll do both sides today. Make sure you're on the right side because the tops kind of look the same, right? You've got this one. That's not the one we're starting on. This one with the graphs. Graphs are kind of hard to see, but this is the one we're going to start with, okay? So we're going to do arithmetic and geometric patterns, okay? You can probably write smaller than me, okay? So that's kind of the focus we are doing here. Okay, is we're taking a look at these arithmetic and these geometric patterns, okay? So, what is that about? Well, it's about helping us to understanding the two main patterns that we're dealing with this year and how they connect to, a little bit more room for this, to equations, to tables, to graphs, even to kind of some story problems, which we won't hit that as hard because we've kind of dealt with that a bit. Okay, so that's the stuff we're dealing with. Okay, we're understanding the two main patterns and how they connect to the equations, tables, and graphs. Again, let the teacher know if you need to have something paused so that you can deal with it a little bit better. Okay, now I'm going to try something here. Okay, good. So I can zoom in here. Might be a little skerwampity. It's kind of hard to get this to match up just right. But hopefully this will allow us to zoom in and give us some more space to write things, okay? So this first one on the left, okay, we're looking at the arithmetic patterns, or pattern, okay? That's what we're dealing with. And now remember, an arithmetic pattern is adding or subtracting, right? We discussed how, or we'll discuss how subtracting is the same as adding a negative, okay, by the same number adding or subtracting by the same number in a pattern, we'll say, whether it's in a table, whether it's just story problem, picture, something like that, okay? So that arithmetic pattern is adding or subtracting by the same number in a pattern, okay? And we haven't really talked about this, but because we're doing these notes today, okay, the arithmetic pattern is really the basis for a linear function. Okay, now that word linear should be one that you've heard before, okay? So it's the basis for a linear function. Now, if you haven't heard the word function before, I guess we could, if you have space, a function is basically just a special pattern, or I guess a special relationship with certain rules. And we'll really get into this later, okay? But just so, we're going to use the word function probably pretty often here, just so you're kind of aware with that. You don't necessarily have to write that part down, but just so you guys were aware with that portion, okay? So now this big box, we're just going to put in a few examples here, okay? Just kind of some examples of what's going on. So let's say we just have some sequences, right? So like 2, 8, 12, 16, and so on. Remember, those dots mean that you are actually, erase that. Those dots right here just mean that the pattern keeps going, right? So we can see we're adding 4 each time, right? So that's one example, okay? Another example would be, we could subtract 50 to 45 to 40 to 35, right? And we can see that pattern would just keep subtracting by 5, okay? So we may see it in a table as well, okay, with our input and our output. So input of -2, -1, 0, 1, 2, 3. Right? We have this 100, 92, 86, 78, 70, 62. Okay. Here we're subtracting by 8. Okay, so a pattern may look like a table. Okay, something like that. It may look like a graph. Okay, where you have a line. Okay, a straight line like this. That would be an arithmetic pattern here. Okay, okay, something like that. Maybe it is a story problem. Okay, so like this. Ivan works at a restaurant. Bussing tables. Cleaning up tables after people leave. Okay. He is paid $7 per hour plus $10 per table he busses. Okay. So maybe we wanted to figure out how much money he could make in an hour based on how many tables, right? So often we have a question, right? How much can he earn in an hour? Okay? So that would be an example of another arithmetic pattern where we're starting with 7 and we're adding 10 each time, right? And so again, understanding that start and that growth is an important feature of this. Okay, maybe we just have a picture, right? We've done pictures before. Maybe it's something like this. Here's the second and the third and the fourth. Oh, I didn't finish the fourth. Very good. All right, and the fifth, and so on. Right? We can kind of guess, if you needed to. Okay, some sort of picture like that, and we can see the pattern, and we can see how it's growing. Okay, and all of these are arithmetic patterns. Okay, they're either getting bigger or they're getting smaller, either adding or subtracting. Okay. Now. Okay, we're kind of going to show a few more examples. I guess if somebody still needs time, now would be the time to pause. I should probably give you time so you can pause and make sure everybody gets this portion done, okay? All right, let's take a look down here. Okay, so let's kind of do a table here. All right. So 0, 1, 2, 3, 4, 5. This is kind of another example idea, okay? Because we didn't put any equation examples up there, but I did kind of want to put this one specifically here. Okay, so sometimes we call this the x. We'll sometimes call it n, but it's the input, right? This side's the output, which sometimes we may call a sub n. Now, if that looks crazy, okay, we're going to deal more with this guy, so don't freak out too much. And we've got the y, or we'll use f of x, which is dealing with a function notation, okay? So let's go to 5, 8, 11, 14, and 17. Okay, so this would be an arithmetic pattern, right? Because we're adding 3 each time. Okay, so for an equation, we might write something like this, right? Y equals our starting number, and we added 3 every time. Okay, so we go y equals 2 plus 3x. We also have another type of pattern, or equation, I should say, that we're going to use. Okay, and we'll talk about this on the back side more, but it looks something like this. A sub 0 equals 2, and a sub n equals a sub n minus 1 plus 3. Okay, both of these equations here are dealing with this pattern that we can see right here. Okay, and just something to highlight here that we will a little more in depth, okay, is all those 2's mean the same thing as well as those plus 3's. Okay, and each of these other pieces actually tie into things as well. Okay, suppose I could go 0 right here, 0 right there, and even the ends, how they match up. Could even do the x's here and the y's. Okay, but if we were to graph this table, if we were to graph this equation, this stuff, it looks something like this, right? Zero, 2, graph right here, 1, 5, 2, 8, 3, 11, and so on. Okay, and our graph would keep going up in that straight line. Now often we'll continue it in the same direction going back. Okay, so sometimes depending on the situation, we will want to mention that this can continue in the opposite, hope I spelled opposite right, direction. Okay, so these are kind of some ways that the arithmetic pattern looks like. Okay, so remember that when we talk about its graph, the graph is simply a straight line. Okay, so that's kind of just dealing with the arithmetic pattern. We're going to deal with all this stuff. We're going to get to the point where we can connect all these pieces together, like with that start and that growth. Okay, how we can see where the start is in the graph, in the table, in the equations. Okay, in the slope, how we can see that in everything, slope or growth. We use those words interchangeably. How we can see all that, you know, in our sequences, tables, graphs, pictures. Okay, all this stuff, knowing that again, it's all part of this arithmetic pattern. Okay, so again, if we needed any more of this, you know, have the teacher pause it. Okay, any one of those, and make sure we have those. Okay. All right, so we are done now with, and that's probably driving you guys crazy that I keep wiggling it. It's because I try to get it exactly straight, but it's just so hard to do. All right, so that's the arithmetic pattern. So next up, what we're going to take a look at is the geometric pattern. Okay, and that's right there. Okay, that's our geometric pattern. So let me zoom in here. This is, by the way, this is posted up on YouTube, so if you didn't get something and you felt weird asking for them to pause it for you, you can go home and finish this. But don't use that as a just to tell the teacher, oh, I don't have to write anything right now, I'm just going to go home and write it down. No, write as much as you can right now. And then if you miss a little piece here or there, then you can go back home and you can do it. Okay? So geometric pattern, That is when we are multiplying or dividing by the same number in a pattern. Okay. Now, generally speaking, we deal more with multiplying than we do dividing. And when we really get to some of the examples and some of the formulas, we like to deal with multiplication, not so much with division, just because of the way division affects graphs. Okay. So, and just like arithmetic was the basis for a linear function, geometric pattern is the basis for an exponential function. Okay? I always forget to put periods when I'm writing on here. Alright, so let's take a look at some examples here, and we'll of course make it super colorful because we can. Well, I can. I don't know if you guys can. So again, some examples if we're just dealing with sequences, just straight up number patterns. We'd have like 1, 4, 16, 64, and so on. Okay. And if we can't see that, we're multiplying by 4 each time. Okay. We could also go with the division one, right? And go 64, 32, 16, 8. And we're dividing by 2. Or we could say we're multiplying by 1/2. Okay, you can say it both ways on that. So that's what we got going there. All right. Can also do tables and put in our output. Okay, maybe it would look something like this. 180, 60, 20, 23rds, 29ths. As if we were dividing by 3. Okay. When we deal with their graphs, one way it can look is like this. Okay. Which down below here we'll do more of that. Okay. Maybe it's a pattern. We would see something like this. 2 dots. Then 6 dots. Then 18 dots. And then, oh wait, that was only 12. There we go, 18. And then we could do that same thing, right, 3 more times to get, what, 24? No, 54, something like that. Yeah, where we'd have the same pattern going on. If I do them quick like that, it's not so bad. Okay, and so on. The pattern could work like that and so on. Or maybe it's a story problem. Okay, so like Liza put some money in the bank. She had $100. I don't know if I need to put dollars at the end, but I did. Total. Okay. It will double every year, which is not too bad. How much will she have in 5 years? Okay. So it could be a story problem like that. Okay. Which, if it's doubling every year, after the first year it doubled to 200, then it would double to 400, then 800, then 1600, and that 5th year would be 3200. Not too shabby, right? If you only had to leave that $100 in there for 5 years. But if you go to a bank, you'd never get a rate that great, okay? They would never, 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 never give you anything that good. It's way too quick of a return on your investment. All right, so pause this again if people still need to finish writing some of this down. We're going to kind of give it the same treatment we did down here. Oh, pause. Okay, should be good now. Do it, but over here, okay? So again, we'll draw that table, remembering that we've got our input and our output. And we need to make sure we understand that they're inputs and outputs, because that'll become critical when we talk about our formulas, our equations. Okay, so again, the many types of notations. Okay. Now, if we were doing a, it's actually, we gotta put our pattern here, don't we? So hopefully we can see we are timesing by 2 each time. Okay, starting out with 2. So if I were to write in the recursive format, a sub 0 equals 2, a sub n equals a sub n minus 1 times 2. Okay, that would be our recursive version, which again we'll talk more about. For our explicit, we could use f of x, which is function notation. Again, we'll learn that later on, but I just kind of like to preview it a little bit here. So we'd go 2 starting times 2 to the x. Okay. So now, the interesting thing about an exponential, a geometric graph, is that the graph is a curved line. Okay, now there's a lot of different curved lines, so it curves in a specific way. So if we graph this now, first of all, I'm going to need to adjust my scales. These will still be 1, 2, 3, 4, 5 to 10. But here, we're going to actually start up here and make this 32. And we're going to go halfway down. In order for the graph to look right, I need to do it this way, 16. So you'll want to label yours the same way. Then I'm going to go halfway between that, which is kind of right about here. That's going to be 8. Then halfway, right about here, going to be 4. Then half of that, which will be about here, will be 2. Okay. So you'll want to label your graph accordingly. Then if we just graph the points, right, 0, 2. Let's actually make it a different color, a little more visible. 1, 4, 2, 8, 3, 16, and 4, 32, and we're not going to be able to put the rest of it on there. So it has this curvature right there. And then, just like with the other one, sometimes it'll come off here to the left. Okay, so it can continue in this direction. Okay. All right, so again, if you need to catch up, have the teacher pause it and get it caught up, and then let's take a look. By the way, don't yell at people if they're taking longer than you take. Some people like to write better than you write, and most likely yours is pretty sloppy if you're done that quick. So, all right. Again, so should look something like this, obviously without the color. Okay, but again, just kind of looking at the difference between that arithmetic and that geometric patterns. Okay, and kind of understanding how those patterns work with addition and subtraction, or multiplication and division, looking at their graphs, tables, sequences, and story problems and pictures, okay, which kind of covers the basic models that we have. All right. Okay, so let's jump to the back side now. Your hands are probably getting pretty tired, and maybe you won't have time to finish this in class, but if you do, then that's awesome, and we'll finish it in class. So let's jump to the next section. Okay, so now with this section, okay, we are going to go with let me get my notes. And apparently I accidentally turned on some music on my computer. I do not know how I did that. That was weird. All right. Anyway, I don't know. You maybe didn't even hear it because it wasn't super loud. Okay. All right. So now we're looking at recursive and explicit equations. Now, when we talk about explicit equations, I don't mean they're equations that swear. Okay, it's not like on iTunes where you have explicit music and not, or other listening programs and whatnot. Okay, it has to do with the type we're dealing with. Okay, recursive generally means something that is using what's happened before to highlight what's happening next. A lot of computer programming is recursive, uses recursion, because it's like, if this happens, then this happens. If that happened, then we do this. Okay, which is all this programming. That's basically everything that's happening. You know, like on your cell phone, if you hit this app, it opens this. Okay, all that kind of stuff. Whereas explicit is more, how do I want to say this? It's showing you exactly what's happening, I guess, might be a way. It's very straightforward. Maybe that's a good way of saying it. Okay, something like that. So, what is it about? Well, this frame is about the parts of recursive and, use my fancy symbol there, explicit equations and using them, I'm going to run out of space, so I'm going up here, to model patterns and relationships. Mathematically speaking, not relationships otherwise. Okay. So, we're going to spend quite a bit of time with these recursive and explicit equations. Okay, so you're going to get very comfortable with them, which is not a bad thing. Okay. So, if you need to quickly finish that, I'm trying to stall for you for a little bit, but then we are going to zoom in and we're going to take a look at each one separately. So basically we've got recursive and explicit. Okay, so again, I'm going to kind of zoom in on each of those so that you can focus just on those parts. Okay. All right. So for recursive, okay, here's kind of the main idea. So main idea is that it connects the outputs of a pattern. Okay, so basically what it does is it models how we think of patterns. Because when I give you a pattern, you're going to say, and I ask you, well, what's going to happen the next step? Well, you're going to use the previous step to figure it out. Okay, so that's what the recursive one is all about. Okay, now it's kind of weird the way we write it down. The concept, I think, is easy. The way we do it, that's where it gets tough. Okay, so you're actually going to need two parts to it. Okay, you need the growth and the start. That should be familiar stuff that we've been talking about. Okay, I guess we could start calling them the y-intercept and the slope, but we're not necessarily going to start using that yet, that language. Okay, maybe as we get more graphing we will. So they will have two separate equations. Okay, so you're going to have two equations that equal one equation. Okay, and we'll kind of talk about why that is a little bit, but for sure later on. Okay, now we've got some kind of definitions of some of the terms. So we're going to have the letter n involved. Okay, the letter n basically stands for the input or the term number. So like the first term, the second term, third term, fourth term, and so on. Okay, we're also going to have this term called a sub n, and that's how we say it, right? It's pronounced a sub n, because n is a subscript. Okay, so that's going to be our next output. Okay, so if we're given a pattern and we want to know the next one, we're talking about a sub n. Okay, now a sub n minus 1, okay, where n minus 1 is the subscript, that's going to be our previous output. Okay, that's like, what just happened? What number do we just have? Okay, that's represented by a sub n minus 1. So I'll say that again, that's represented by a sub n minus 1. We also have a sub 0, okay, which that's going to be the starting output. Now, the thing about a sub 0, which I don't want you guys to write this down yet. No, I'll do it later. I'll do it later. Okay, so let's kind of look, so we can do recursive equations for both geometric and arithmetic. So let's kind of look at the example real quick of arithmetic or a linear pattern. Okay. So we are also going to do a geometric or exponential pattern. You're going to see they're basically the same thing, but I do like to highlight the fact that there's both of them. Okay. So you may want to pause right now so you can kind of pay attention to this next part. So if somebody needs a pause so they can catch up, we can do that. All right. All right. So the first part of the equation would be the a sub 0, and that would equal the start number. And normally in place of the start, I would put a number. The second part of the equation, or the second equation that makes up the recursive formula, is a sub n, our next output, is equal to a sub n minus 1, our previous output, then plus the growth. So if I'm adding 2, we'd put a plus 2 there. If I'm adding 5, plus 5. If we were subtracting, I'd put a minus 10, or a minus 3, or a minus 1 million, whatever it is. Okay? And that whole thing together makes up the equation. Okay? So we have the starting part, and then the growth. Okay? So this represents our start, this represents our growth. So I know, kind of weird, but that's how it is. Now for the geometric, it starts out the exact same way. A sub 0 equals our start number. Okay? Then it keeps going the same way. A sub n equals a sub n minus 1. To get our next output, we take the previous output. And this time, because it's an exponential or geometric, we're going to multiply by the growth. Ideally, we could also divide by the growth, but we just want to get into the habit of multiplying instead. And when we get to the explicit equation over here, it'll make more sense as to why we do that. Okay? But again, these together make the full example. Okay? So if you need to catch up, pause it. If not, let's move on and kind of talk about more about it with this example idea. Okay? So let's write some stuff down first. So we've got arithmetic, which we've got a table here, and a sub n, and we've got geometric. We're going to have another pattern here, again with n and a sub n, and let's actually fill this pattern in. We'll fill the other pattern in too. I'm actually going to erase a little bit of that. Or maybe I'm not. There we go. Do a super simple pattern here. Those are question marks, by the way, down by there at number 6. Okay. Now, let's kind of use that basic up here. So really, I've got a sub n equals my start number. I've got a sub n, a sub 0 here, sorry. A sub n equals a sub n minus 1 plus or minus the growth. Okay. So now I'm going to color code my stuff to help make it make sense, but I'll try to draw the arrows so it helps you guys out, okay? So a sub 0, okay, let me grab a different color. So this 0 here, it corresponds with that 0 right there, okay? Notice how we've got the a sub n here, and the n. That corresponds to that input category, okay? So that's part of what's happening, okay? It's part of what it's dealing with, okay? So this a sub 0 here, draw an arrow to it, represents that 0 right there. And the start number is represented in the output column, okay? Because that's what we're dealing with. We're dealing with outputs, okay? That kind of tells us what our starting output is going to be, okay? So if I'm to rewrite that, I would write a sub 0 equals 3. That would be the start of my equation, okay? And actually, yeah. Now, the thing with the n's, okay, this whole n represents, okay, and I'm going to have a ton of arrows, that column. But a sub n together, and this is where it gets kind of weird, actually represents this column, okay? That a sub n, or that a sub n minus 1, it represents the output, okay? So when I say a sub n, I'm talking about a number, an output, okay? I'm not talking about the n, okay? And I know that's weird to think of, okay? Now the growth, okay, the growth here is represented by our growth here, which we're adding 1 each time, right? So that would be our growth. So to write my next part of the equation, I'd go a sub n equals a sub n minus 1, and then we're adding 1 each time, okay? And that would be my formula, okay? It's got the start, and it's got the growth, okay? So, again, that a sub n, okay, that represents the next term, okay? So say, like, looking at my little example here, I'm looking at this. I want to know what the question mark is. That's what a sub n represents, okay? And so that n would be the 6th term, so that represents the next term. Because I don't know what the next term is, so I'd write a sub 6, okay? Which tells me this is where I'm dealing with. This is the number I'm looking for at a sub 6, okay? So where things can get super confusing because of the way that things are written. Now, to figure that out, what do I need to know? Well, I know that n is 6, so I'm going to have a sub 6 minus 1, which we're going to add 1 to it, right? Now, do I know what a sub 6 is? No, I don't. It's a question mark. Do I know what a sub 6 minus 1 is? Well, a sub 6 minus 1, right, because this represents the previous term. Right, which you can see up here. Because what's a sub 6 minus 1? Well, 6 minus 1 would be 5, so I really have a sub 5 plus 1. Like I said, the a sub 6, a sub n, a sub 5, when I say the whole thing, that's the output. So what is a sub 5? Well, it's 8. So this we can actually replace with 8. So we have question mark equals 8 plus 1. Well, what's 8 plus 1? It's 9. So what does a sub 6 equal? It equals 9. Which, you're probably looking at me saying, well, duh, Mr. Radolch, okay, I could have just looked at the table and told you that. And I know that's true. But I'm teaching you not how to find the next number. I'm teaching you how we mathematically represent that. Okay, which it looks super ugly, but that's just the way it is. Okay? That's just the way it is. Also, we probably want to mention that this plus 1 up here is the growth, right, that we see in the table. So if the table was plus 5, that would be a plus 5. Something else to also mention, and you don't have to write this part down, right? How I said a sub 0 represents the 0 there. Well, it was equal to 3. Well, I could say a sub 1. What would a sub 1 equal? Well, it would equal 4, because here at 1 we have 4. A sub 2 would equal 5. A sub 3 would equal 6, and so on, okay? But we like to really use a sub 0 first because it helps us when we get to the explicit. You'll sometimes see people say use a sub 1 instead, and that's okay to use, but that's the way we do it, okay? Now, for the geometric, same exact idea, okay? We have a sub 0 equals our start number. We have a sub n equals a sub n minus 1 times our growth. If I look at this one, again, this 0 is represented here, so I'd go a sub 0 equals 1, okay? Again, that start, right, connects here. The growth here times is represented in the fact that we're multiplying by 3 each time, okay? And the a sub n is that next term, and the a sub n minus 1 was that previous term, okay? So, if I'm writing my formula, a sub n, because I don't put the numbers in for this part of the formula, a sub n minus 1 times 3. Now, if I want to use it, okay, that's when we would do stuff. Say again, I wanted to find this 6th term. So I know that I start at 1, and I know I'm timesing by 3, so I'd go a sub 6 equals a sub 6 minus 1 times 3. 6 minus 1 is 5, so it would be a sub 5 times 3. Do I know what a sub 5 is? Yeah, it's 243. Times that by 3, and we get 729. So a sub 6 equals 729. Okay, again, if we're doing a table is definitely easier to do. So we're not going to require you to like mess with this kind of stuff on equations, okay? We're just going to actually be writing the equation based on a table or a graph or something. So the main idea here again is that a recursive is helpful in finding the next term. Okay? So, I know that was probably a lot to take and pretty confusing, but we're going to be dealing with this, so we'll have time. I don't expect to come tomorrow to class or just next time I see you to think, oh, you know exactly what I'm talking about now. No. This is to use to help us, and my arrows are probably like confusing the heck out of you. So, yeah. Anyway, get this written down. We can refer to this as we're looking at other stuff, okay, as we're learning and going. These notes should be used notes, not just, we don't write them just to write them. We write them so we can look at them to use them as we are working on our problems. And maybe as an incentive for that, I'll say that something like, I'll have to talk to Mr. Vorwaller about this, but he'll probably agree with me. Maybe we'll let you use these notes on the quizzes or tests or anything like that. If we're going to take the time to work on them, maybe we need to take the time to use them as well. Okay? So if you still need this, ask your teacher to pause it, and then we will jump over to the next one. All right. Explicit. Again, we're not swearing, okay? So it's just a type of an equation. Okay, now the main idea here is that it connects the input with the output. Of a pattern. So recursive, we're connecting outputs. Now we're connecting the input with the output. Okay? Also, so we still need the start and the growth, but they will be in one equation. Okay. which now the explicit is the one that you're probably going to be most familiar with, okay? One that you're going to be most familiar with here, so, which is good. It's the one we've dealt with before this year. It's the one that you've probably dealt with multiple times in previous years, okay? So what we do here is it uses the pattern, okay, or the growth, so we don't need previous outputs, whereas recursive doesn't work, okay? Because, speaking of, I'll go back to this. Speaking of, if we wanted to say down here, actually, let's do this. I wanted to find the 100th term. Okay, I can't just figure out the 100th term. I have to go through till I get down to the 99th term to be able to find the 100th term. Whereas with explicit, that's going to change. That's going to be different, okay? So it uses the pattern, so we don't need previous outputs, period. Okay, so we use things such as a variable. Whereas technically, I know I'm jumping back and forth, these aren't variables, okay? I wouldn't call those variables. Those are terms. They represent terms. They represent numbers. They represent positions, okay, on that pattern. Whereas with this, we use a variable. Typically, we use x, and that is our input, okay, or our term number. Okay. Then we use the y variable, okay, or if we're doing function notation, f of x, and that's going to be our output, okay? So x is input, y is output. X is input, f of x is output, okay? That's how we're going to take a look at those ones. So again, we're going to use our arithmetic example, okay, / linear example pattern. Crap, writing the wrong thing here. Hopefully I was ahead of you guys so you didn't make that mistake either. Okay, we also have our geometric or our exponential pattern. All right, so for the arithmetic, I'm going to give you kind of two different versions and two different versions of those two different versions, okay? The one you're probably most familiar with would be this one here. Y equals mx plus b, okay? I also like to think of it as y equals a plus b to the x, or b times x, okay? I like to do the start number, then the growth, and that's kind of how I've done it a lot of times. Now, if we're doing it in function notation, everything looks the exact same, except for instead of y, we use f of x, but everything else looks the same. Okay. Now, for the geometric or exponential pattern, we have y equals a times b to the x, or f of x equals a times b to the x. And it's because we write it this way that I like to write it this way, because I think it connects things better, and then it makes it so it's a lot easier to create an equation. We don't have to figure out, oh, is it geometric or arithmetic? I start it the same way, and then when I look at the pattern, that tells me is it geometric, is it arithmetic, and boom, I go from there, okay? So that's how I like to do it. All right, so if you need time to pause it, then pause away and get this written down, and we are looking at the last part. We're almost done here. I know your hands are dying. Just be glad you didn't have to write it twice like I did, okay? Unless you're writing it twice, then welcome to the club, I guess. All right. So we're going to kind of follow that same setup we did on the other side. So we have an arithmetic. We have a geometric. We're going to have a pattern here, or a table. This time geometric will be x and y. Those 3 dots mean there's stuff going on that we are not showing. Okay, there is our geometric, and now our arithmetic. We'll do function notation on this one just to throw you guys off. It's actually, I do that with a purpose. It's just to let you know that it's all right to use those interchangeably. Notice that I didn't put the 6th term like I did on recursive, because that wouldn't make sense, because it would be way too easy. All right, so there we go. And for arithmetic, right, we start out y equals mx plus b. We'll use that version because you're probably more familiar. And f of x equals a times b to the x. Okay, now again, using my awesome powers of color codeness, okay, the y here, same as f of x, it represents the output numbers, okay? So whatever number I get for y would go in that output column, okay? That was a good way of saying it. I never said it that way. I hope that helped make sense, more sense, because I just thought that's a cool way of saying it. We also have our growth here, the m, right? Which, in an arithmetic, we often call our slope. The growth, we can see we're adding 1 each time. There is our growth, okay? Now the x actually represents the input number. So whatever number I stick for x is an input, and then I get a y, which gives me the output. Okay, we should hopefully see a connection there. Okay, now this b is our y-intercept, okay, which the way we can see it is it's that number with 0. Okay, so it's our y-intercept, or we can call it our start, same thing. Start slash y-intercept. This was our growth, right? This was our input and our output. Okay. So if we're looking at this pattern here, we would say y equals, my growth is plus 1, so just a 1, positive 1, times x, and we started at positive 3, so plus 3. Which again, I usually would write it like this, y equals 3 plus 1x. I think that makes more sense, but same thing. Okay, now if we want to use it to find the 100th term, which we couldn't really do with our recursive, because the explicit is helpful, critical really, in finding any term. The way it's set up, it allows us to find any term. That's like a 3 exclamation point. Okay? Whereas back over here was helpful just in finding the next term. Didn't help us when we got clear down here and we wanted to skip a bunch of stuff. Only helpful in finding the next. Whereas this one is super helpful. Super, super, super helpful when it comes to figuring out this 100th term. So this 100 is in my x column, which means I replace my x with 100. So 1 times 100 plus 3 is going to equal our output. 1 times 100 is 100 plus 3, 103. So what's our output here? 103. All the students yelled out in a chorus. Exactly, 103. Okay, so the explicit one probably seems a lot more simple, but you've dealt with it a lot, so it does seem a lot more simple. Okay, so don't get hung up on that recursive, not arithmetic, because we just did arithmetic. That recursive formula and all its weirdness that it has going on. Okay, now if we look at the geometric, okay, this f of x again represents the output, okay, for a function, okay, and it means any output number, right? So it could be 1, 3, 9, 27, 81, 243, or any other number as long as it fits into our pattern. Okay. Now here the growth is actually b. Okay. So that is our growth, which in this case is timesing by 3. Now, and that's why I like to do the y equals a plus b x, because to me that follows this, that makes your arithmetic and your geometric kind of the same setup. And I really like that. Now a here is our y-intercept, or our start number, so it's where this is 0, so it would be 1. Okay, so that's our start. Also, we call it the y-intercept as we get graphing. This was our growth, right? Gotta label this because you guys can't do colors like I can. This is the output. And so the x up here is our input, representing any one of those numbers. And based on whichever number we choose, that's going to tell us what our output is, right? So again, if we want to use it, or to create this from the table, we say f of x equals, oh, P.S. This x here is actually the input as well. So I go f of x equals a, which would be our start number, which is 1, times b, our growth, which was timesing by 3, raised to the x power, right? Because repeated multiplication is an exponent, right? Repeated addition is multiplication. Repeated multiplication is powers. Okay? Now, let's say we wanted to use this to find the 10th term. I do the 100th term, but it's way too crazy big a number. So the 10th term, so I'd say, all right, I'm looking for that 10th term. My input is 10. What's my output going to be? Okay, so 3 to the 10th is actually 59,049 times 1 would be 59,049 is equal to our output with an input of 10. Okay, so again, telling us what that number is. And again, if I was using recursive, I'd have to go a piece at a time till I got there, which sometimes, especially with geometric, sometimes that's kind of the route to go because it can be easier to deal with. All right? So, okay, awesome. So we got a lot of stuff here, okay? Dealing with a lot of stuff. So now, one thing to just mention about the recursive, okay, and I'm just going to, I don't know if you have space down here on the other one. Write this somewhere, maybe up at the top. Okay, recursive can also be in function form. Okay, and it would look like this. F of n equals f of n minus 1 plus or minus or times the growth. And then it would be f of 0 would be our start number. Okay. All right, guys. So there we go. A ton of notes here. So yeah. So we will call that good, right? Again, if you need to go back and get anything that you missed, do it. But there we go. So that is awesome, and we'll call that good.